at our final presentation. Super excited on the topic of digital twins again. So we have standards-based digital twins with flexible IoT solutions. Kjell Bengtsson from Jotne. So take it away, and appreciate you presenting.
Thank you, David. So thank you for having the opportunity to present to this team today. So this presentation is developed by myself and also one of my colleagues, Dr. Remy Lanza, who have been working on this subject for some years now. So myself, I've been around in the STEP ISO 10333 arena for quite some years now. I work with, I would say, leading OEMs. We also do a lot of research that I oversee. Dr. Remy Lanza, he is, you can see on the pictures, he's one of the young kids. We sponsored his PhD thesis now at the NTNU University in Trondheim. And he recently completed his thesis in what's called capture and reuse of engineering knowledge and digital twins. And in that project, we also had the opportunity to work with Lockheed Martin. So thanks to Lockheed for overseeing this PhD study. He worked in the what is called the AP209 development, which is related to finite element work and so forth. So I will get back to that. And our company, those of you who do not know the company, we work in various sectors like aeronautics, space and defense. Similar to the STEP community, you also have in the built environment the IFC or Open BIM. So this is what we do. We develop solutions for this kind of industries and provide software solutions to these companies, not only to big companies, but also to other software vendors like PTC, Autodesk, and other engineering tools providers. And just to capture a little bit where we are in this environment, we contributed to this AI document 10 years ago, the Aerospace Industry Guidelines for Implementing Interoperability for Standards for Engineering Data. And since then, you know that the AI had developed a new position paper on digital twin, and we adhere to these kind of documents. We love them, and we also see what they are heading for, and are now about to developing a new support letter, which is called a digital twin implementation position paper. And if you look into these documents, the recent documents, is that what we found very encouraging is that they are addressing the digital twins across the lifespan cycle and also the supply chain. Assuming that there will be a number of digital twins in the supply chain and they need to communicate in some way or another. Also see that they encourage open standards, both for data and its models, and that is something that the people like us adhere to. And also that this should be open, this foundation. So we work in this community for many years, and we try then to develop solution that fits in for the purpose here. In the aerospace industry, people like Airbus, Leonardo, BAE System, that piloted using the ISO 10333 standards more than 20 years ago. In the Eurofighter project, I do the configuration data management since then, and still using the same type of data exchange processes for the Eurofighter jet fighter. Equivalent, also Lockheed Martin use it for their various programs, and they have been using this for many years. Reported in 2018, they have about 500,000 step files, and I assume since then even more so. If you look into the right-hand corner, you will see that most data exchange processes in this community is using the STEP standard. So more than 80% of the data exchanges is based on the STEP standard. So that again shows the success of the STEP standard per se. When it comes to the digital twin, we have another type of opportunity. Maybe we're not able to exchange CAD data, PLM data, and also the simulation data, right? However, if you're then going to put this kind of data in the hands of an AI or machine learning engineer, and at the same time collecting a lot of data coming from sensors, they will have a nightmare because maybe they don't understand the data that they will look into. Maybe the quality is not there, and they have to spend about 80% of their time to discover the content of the data and fix the quality of the data. So we need to help these smart people coming out from university to be more efficient, to get to the point where they can, make the new generation of software applications for AI and machine learning. So that is one subject that we need to address. We need to support these teams getting access to this data. Next slide is somewhat similar, because you will have a lot of different kind of sensors out there, and you will understand that first you need to connect the data, you need to use some IoT software, you need to have a reference data library of applicable sensors, you need a gateway, you need a PLC. So there is a lot of interconnection problems that you need to look into as well. And we will address these kind of issues when we go forward. As you know, ISO 10333 have been around quite some time now, started already back in 94 for 3D CAD models. PLM was introduced in 1999, logistic support in 2005. And recently we see the merge of AP203 and AP214 to the new kit called AP242, which is in sync with AP209, which is used for finite element model. What you can see here on this winglet, you can see not only the CAD model in gray, you can see the superimposed finite element results coming from Abacus, and you can also see the sensors being populated there as the hair crosses. So this is what is possible today. And we envision that you should then be able to collect all this data in one common repository from your early design phase of your CAD models, your simulation model, manufacturing models, and then when you connect the sensor data as well. So this is what we think that ISO 10333 can offer today. We have also looked into how can we do this, because it started out when you could then identify how to store the sensor data in AP209 at the small hair crosses there, and that was the key, I would say, opening to connect all this kind of data into this repository. And you can look into the ISO 10333 being a quite complex data model, and if you're interested in the objects where you could store the data, like in the breakdown element have an ID, and the ID have this serialized ID for the sensor, and to the right there you see some kind of key attributes for this sensor. We have its timestamp, acceleration in X, Y, Z, it have a battery, humidity, pressure, and the signals and so forth. So this is how we have implemented the sensors into ISO 10333, and for the reference data library of sensor characteristics, we're using a complementary standard called ISO 12006 to store and manage the meta model of the terms and definitions. Very equivalent, we also support other big organizations. This is from the European Space Agency, where they need to create digital twin for validation. So in addition to support AP209, we need to support specific tools like thermal tools, like radiation tools, only being of interest for the space community. And we need to convert all this data into AP209, in addition to taking care of the sensor data. So to the left here, you see a full-scale satellite, and you see the test bank where you put in the vibrations for the satellite, which will have to withstand about 10 minutes of heavy vibrations. And all this data is then collected into a correlation tool. And this is what you could do with ISO 103 today. And Remy here wrote his paper, and you can download the paper here showing how you can store your sensor data into AP209. Equivalent, we work for other companies, and this is another space program where we have to create a digital twin. And the purpose for this is also to do I would say a benchmark for next generation of production. And here is the radiation is the key here, because it's a low orbit satellite that will have this component on board. So we have to develop new systems for that purpose, and we are looking into next generation of additive manufacturing for this kind of components. And you also see that from pictures from the test lab, where I put a lot of radiation on top of the electronic to see if it can withstand the conditions. So with that, I would like to summarize a couple of experiences that we have been doing in our R&D activities. We have a number of R&D efforts. We have, I think, 7 big programs, and here is some of them, and you can have a look on them on the websites to find out more about them. We have developed digital twin, and this is quite interesting. This was the baseline for a prosthesis that you put in for runners that only maybe have one leg only, and we need to optimize this. So here you see some of the optimization process, and also for the testing and collecting all the data to be able then to do the correlation and validation of the new design. And as mentioned, we have then demonstrated how you can do this in one single repository, from the CAD simulation and also sensor integration from the test campaigns for that purpose. Another one that is more manufacturing oriented, this is a lathe machine, and it contains about 30 megabytes of step data. It have about 11 sensors. You see one here, you see another one here, you have a finite element model here. So what do we want to do here? We want to do the correlation from the simulation of the tool and also to the collected data. By the way, there is a presentation coming up in October, so if you're very interested in manufacturing digital twin, you should listen in to Marianne that will do her presentation on that subject. So what can we do this? What we did do was that we imported this CAD model into the repository. We connected the sensors, and in less than half a day, we could then populate the sensor data from here. So what you see here is the sensors, the 11 sensors, and the dashboard of the sensors, where you can then collect all data into the repository. And when the data is stored in the repository, you can then very easily start to do your AI stuff, your machine learning, to improve the manufacturing processes. So just to say to people being interested, so starting point was the CAD model of your system or a manufacturing unit, and loading that into the repository, connect the sensors. So it's a 3-step integration work. And if you have good programmers that understand the basic of, let's say, JSON and other type of technologies, REST APIs, it's quite easy for them to do this kind of integration. Very equivalent we do for water power solutions, where we have some use cases where there is vibration on the turbine and its generator, and we are then populating with other type of sensors, not necessarily only vibration, but also acoustic sensors, like in thermal cameras as well, to store all this kind of data. So this is how we envision that you can do for your own systems and components as well. So going back to the integration work, we have been looking into many different kind of IoT software that is around, both commercial one and also academic versions, open source, and so forth. So for the last couple of years, we have been working together with a team called the Arrowhead Tools that had developed an open source. They're now part of the Eclipse Foundation software. And we have quite some good experience in this. So we started out with populating a mountain bike with a number of sensors just to learn a little bit about it. We had this running for 6 months, and then we started to do the real-life implementations. There is a lot of tools around, and you need to look into them yourself, because there is a lot of different kind of implementation methods. Maybe you're interested in WebSockets, maybe you're interested in MQTT, you need to access UPC UA, and so forth. So you need to find out what is your requirements, what kind of system do we have installed, and so forth. And there is a report that you can see there that's actually being updated now, so there will be a newer version around. So you need to find out what kind of connectivity you need for your implementation. So going from the mountain bike with these sensors, we were then able to use the same ISO 10333 repository to develop the digital twin, and also for this crane. So the use case here is the crane, which is mounted on an offshore vessel, as you can see here. We populated. Sorry?
Excuse me, this is Rob. Yeah, we just have 2 or 3 more minutes left. If you'd like to entertain a question or two, then we just need
okay.
Okay, thank you.
No,
thank you.
Yeah, so this is the number of sensors that we put into the crane, and just to show you how this have been working is that we then populated with the sensors, the cloud, and the gateway to allow us then to connect to the IoT framework, right? So this is how the implementation looks like, and consists of these components here. And from that, we can then do the dynamic simulation from the crane and its related sensors. And we have about, I think, 3 million degrees of freedom in the finite element model to do the virtual connections to the sensors. So here is typical data that you can retrieve out from the repository. And I just wanted to show you some real-life pictures, and also then to end up with another short video where you can actually see what is happening on the ship, and the data is then retrieved directly out from the repository. And on the picture to the right here, we can also read out the data, and then to populate the robot mimic the movements on the crane as well. So maybe I stop there and open for questions.
All right, thank you very much for that presentation. Yeah, with just one question. As we look at the Internet of Things, digital threads and digital twins, do you see those concepts moving together, consolidating, or do you see them remaining separate as we move forward and having their own distinct development paths?
No, I think that these two, I would say, viewpoints of a product needs to be integrated, right? Because we see that the digital thread might be version control and connectivity and so forth, whereas the digital twin have another viewpoint of that. And so I think in the long run these have to be merged, these concepts.
Okay, very good. Well, with that, we appreciate your time and your contribution to the GPDIS conference today. Thank you very much.